All right. So let's get going on our electrochemistry stuff um, and see where we end up. Uh, so if you're following along kind of on the GChem website, we're in the electrochemistry section right now. Yeah, I'm not super worried about batteries. Um, I would like to get at least a little bit into potential and free energy. I doubt we'll be able to do that today, though. Um, but yeah, at the very least, we'll get through electrochemical cells today. And then we'll kind of, I'll send an announcement kind of highlighting what's going to go up for the exam and what we're going to do in the Monday before Thanksgiving and the Friday and Monday that follow afterwards. But let's get going. We still have, I think, more than enough time to finish this stuff. We won't do any kind of extra stuff. So sometimes we'll cover like nuclear chemistry, or I'll teach a little bit of organic chemistry or something at the end of the semester. But we're not going to do that this year because these are unusual circumstances. We're just trying to get through the semester here. All right. Did I not post LEs? I posted a couple of LEs. I doubt I'll post more. I don't want to overburden you guys over the holiday. Try to take a break. I'll take a look and see, but right now, just assume there's only going to be a couple. I don't want you to be overburdened by, I don't know, electrochemistry over the holidays. I don't know what you guys are doing or what the current CDC recommendations are for going home for Thanksgiving, or if you're already home or whatever, but certainly don't need the additional stress of oxidation reduction on your plate. All right, let's get going here. So we've been talking about redox reactions, and so the main or a major application for redox reactions are batteries. And so a way to set this up, a way to set up an electrochemical battery, this is the way batteries work in general. So any kind of like your cell phone battery or computer battery, or batteries that you use to run like a TV remote or something like that, run off of the basic principles that we're going to kind of explore here, even though those batteries look a little bit different than the ones we're going to draw. So what I'm drawing here, so these are kind of like beakers, and these are our electrodes. This is a wire connecting these two. And then we would fill it up with some sort of solution here. So let's say that we have zinc over here, and we've got silver over here. And these electrodes, let's say this one is made of solid silver metal, and this electrode over here is made from solid zinc. And so this thing connecting it here, this is a wire at the top, so electrons can flow along this wire. So I can have electrons that flow there. And then this thing in the middle is this salt bridge. And I'll explain what that does in a bit. It sort of doesn't really participate in the chemical reaction. It's just there to keep charge balance. Okay. All right. So if you set this, let's say you set this apparatus up. So I take a solid piece of zinc, so zinc metal, and I attach a wire to it. On the other side, I put silver, so solid silver metal, and I dunk those into two beakers that are separated. So I've got a beaker over here, and I dunk the zinc electrode into here, and I have zinc ion dissolved down here. So some sort of solution. We could say it's zinc nitrate or something, but I'm going to leave the spectator ion off just to clutter things up. You'd have zinc nitrate or something in here. On the other side, I'm going to plunge my solid silver into a solution of silver plus. And so what I really have here, if I remove the wire, I've got two half cells. So these half reactions that we've been dividing things up for the when we're kind of balancing our redox equations. We know that zinc can be oxidized to zinc plus 2 And we also know that silver can be reduced to silver 0. So these are kind of the reactions that we're imagining here. This would shed 2 electrons. We could pick up those 2 electrons over here and have this sort of reaction happening. So the overall reaction for this would be zinc plus 2 silver. And I'm not going through and balancing this the way we talked about. I'm just kind of writing the balance reaction out to begin with, so we can kind of jump ahead here, because those take 15 minutes in and of themselves. So in order to get this reaction to proceed, though, that's what this wire here does. So when I connect these 2 things, it allows electrons to flow between these 2 electrodes. So at this over here we have our oxidation. So there's a lot of information on here. We're eventually going to kind of get this whittled down into a very simple diagram. But oxidation occurs at this is what we call the anode. On the other side, we have what's called the cathode. That's where the reduction occurs. So you've probably heard the terms anode and cathode before. And so the way that they're defined is the anode is where the oxidation is taking place in the battery, and the cathode is where the reduction is taking place. So when you look at the battery, and it'll have like a positive on one end and a negative on the other end. The positive side is the cathode, and the negative side, you draw a negative sign. The negative sign over here would be the anode. So when you're looking at like a a Duracell battery or something, that's what those little signs on there indicate. One's indicating the cathode and one's indicating the anode. Anyway, so when we connect this reaction happens spontaneously, where electrons will flow from the zinc over to the silver. And that's kind of what we're describing with this reaction down here. We're saying that zinc is going to give up some electrons to silver. So it's going to lose electrons. It's being reduced. And silver is going to pick those electrons up. Sorry, zinc is being oxidized. And I get confused with language. Sorry, zinc is losing electrons, so it's getting oxidized. Yeah, this is electrochemical. You definitely will not need to have the activity series memorized. Yeah, it doesn't matter. With the wire is made of something that can conduct electrons. That's inert platinum or something. I don't know. But yeah, so zinc is losing electrons, so it's being oxidized. Silver is picking it up. And so what this looks like in the electrochemical cell is these electrons that are kind of flowing on the little wire. You can imagine them when they get onto the anode. You're building up negative charge. I'm sorry, on the cathode. I really got to get this language down. When it's building up over here on the cathode, so electrons are flowing naturally from the zinc. And now I've got like sort of an excess of electrons over here on the cathode. Those electrons will get picked up by the silver that's dissolved in the half cell. And silver will deposit onto this solid silver electrode. And that's what we're describing in this reaction down here. We're saying we have silver plus, which is aqueous. It's dissolved. And then as it picks up electrons, it turns into a solid. And so once I connect these things, I start this chemical reaction. Now these ions are going to migrate out of solution and just deposit onto the silver electrode. And so you would actually, you could measure the weight of, or the mass or whatever of this electrode at the beginning of the reaction, and at the end of the reaction, it would weigh more because you deposited silver onto it. So it goes from silver plus to silver 0. And then on the other side of the reaction, at the anode, we have sort of the opposite thing happening. So as electrons flow towards the cathode, they have to come from somewhere. They're coming from this electrode over here. They're coming from this zinc that's up here. And so as that zinc loses electrons, it's no longer zinc 0. It's going to dissolve into the solution. So I'm losing mass at this electrode. So this electrode is slowly dissolving in solution. As the zinc gets oxidized, it's losing electrons over here. So I'm losing mass over here. And as the electrons flow over here, this silver is depositing onto the cathode over here. So I'm picking up mass over here as I gain these electrons. And that's essentially what's happening inside of a battery. So once you complete the circuit in a battery, so you put the battery in, you hit the on switch or whatever, electrons are now flowing between the anode and the cathode. As these electrons flow, and this is we might get to this eventually. You can calculate exactly how much work and stuff can be done. But as these electrons flow, what's happening here is there's a potential energy difference between the anode and the cathode, and so the electrons are flowing over here. We can harness the energy, like as these electrons lose potential energy, we can harness that energy to do work. And that's how your computer monitor or whatever, if you're working off a battery, or your phone is staying on. You're harnessing the work that's done as the electrons move from a high state of potential energy to a lower state of potential energy. So the zinc is holding the electrons over here. The potential energy is lower if silver is holding the electrons, and you're just harnessing that power. It's similar to like if you were to take a rock or something, like a boulder. What's a good way to put it? Yeah, if you had like a rock or something up here at the top, and I push it off the side of a cliff, it's going to want to fall down here to a lower state of potential energy, just because it minimizes the gravitational potential energy. But as that rock is falling off the cliff, if you had some sort of turbine or something set up over here, something like this where you could spin it, that's a terrible looking turbine. But if I had something set up right here, I could use the rock to do work. I was trying to draw like the wing of a windmill or something, but I could use the rock to do work on something as it's falling, right? Or if this was a waterfall or something where I'm changing potential energy, so like how these hydroelectric type things work. If I have a waterfall that's falling, as it falls, and it changes potential energy, and it kind of sheds its high potential energy for low potential energy, I can use that to turn a turbine and generate power, or do work on something. This is my waterfall over here. So anyway, so it's easy to imagine when you're imagining a large physical system that you're getting work off of. And it's not any different here, even though we're trying to imagine this microscopic thing that's happening. The electron, in a sense, is falling from a high state of potential energy to a low state of potential energy. And we're harnessing that difference in energy to do work and power our electronics. And this just describes the chemical reaction. There's a lot of different types of batteries you can build. This is naturally not the type of one that you'd use in a phone. We have lithium-ion batteries. So what the hell does the salt bridge do? The salt bridge is just there to keep the charges balanced. So as, let's say, silver over here deposits onto the silver electrode, I'm going to draw out, naturally we don't just have silver plus in there, we have something else. We have nitrate over here. Let's see. Yeah, so you might have nitrate over here. So as this deposits, so like let me explain this a little more because I know this is often a point of confusion. Silver nitrate soluble, yeah, silver nitrate soluble. you can't just dissolve silver plus in a solution. Like if you go and try and buy silver plus at the store, it doesn't, you can't just purchase that. You have to buy the salt. And so you buy something that has it's always going to have some sort of counter anion or something on it. And that's where the nitrate comes in. So, you know, I'd have silver nitrate. Over here, I wouldn't have just zinc. I'd have probably zinc nitrate as well in solution. In either case, these are just spectator ions, which is why I didn't draw them. But as the silver deposits on here, I start to run into this charge balance problem. So at the beginning of the reaction, I have exactly the same number of silver and nitrate ions in here because I dissolved up, you know, 1 mole of silver nitrate. So I have 1 mole of this and 1 mole of that. But if I start depositing silver, I'm not depositing nitrate as well. So just silver is depositing on that electrode there. And so I get this buildup of negative charge inside of this flask. And so if I continue to have buildup of negative charge in there, that's going to screw up this reaction. The electrons are no longer going to flow down here because I have this charge separation. And so all the salt bridge does is keep that from happening. So potassium ions will flow into this flask as silver is deposited to stop negative charge from building up, to stop this charge imbalance that's happening here. And the same is true over here. As I start to deposit more +2 ions in here, I'm building positive charge here. And so nitrate will flow into this one to make sure that charge doesn't build up. And this is pretty much the basics of how a battery or an electrochemical cell works. So we refer to this as an electrochemical cell. You'll also see it called, I should probably capitalize, a galvanic cell after some dude named, I don't know, Galvin. Or you might call it a battery. So when your battery is all charged up, this is what's happening to power your electronics. Let's see. Yeah, so a shorthand notation that captures a lot of this. So this gets pretty messy to draw, but you should definitely be able to kind of label this and understand what's happening at all the different points. So you want to be able to understand the half reaction that's happening at the anode, that it's an oxidation, that this thing's losing mass, you know, that the salt bridge is there to keep the charges balanced in the direction that electrons are going to flow on that wire. So you should be able to kind of understand what's happening here. If we want to encapsulate all of that, yeah, we're going to talk about platinum electrodes in a second. That's a good question. If you want to encapsulate all of that knowledge into a shorthand notation, you can do it very easily. You draw out the anode reaction. And so you can see I've drawn it out just like it happens in the half reaction. It goes from zinc 0 to zinc +2. So I'm just kind of drawing it from left to right. This double line here represents the salt bridge. And then we just write the cathode reaction or the reduction on the other side. And this little simple diagram down here encapsulates the entirety of kind of what's going on in our cell up here. So you'll see these written out in a bunch of different ways. This is like the most reductive way to kind of write it. Reductive is probably not the right word to use here, but this is the most simplified way to do it. You can also have, you'll see things where it has the concentration. I didn't tell you any concentrations here. You know, it might say 1 molar there. You can also have states. You'll see things written on there like aqueous and solid. So you can cram more information in there, and then you have the rest of the other reaction, same kind of thing. You can put more information in there, but at the very least, you'll see this, which at least tells you the reaction at the anode and the cathode. Okay, so not all oxidations happen, or reductions for that matter, happen with a solid. So here, you know, we have this luxury sort of that zinc is a solid, and we're doing this reaction where we're oxidizing it because it's zinc plus 2. And so we can make our electrode just strictly from zinc. And over here, we're doing the reduction. We have silver, and we can make, which is a solid metal, we can take silver 0 and we can deposit silver over here to do the reduction. But we've seen reactions where you don't have anything that's a solid. So for example, if instead of, let's say instead of zinc, you were doing a reaction like this. So this is getting into, this is going to talk about platinum electrodes. Usually it's platinum, yeah. So let's say I have this reaction where I'm looking at, so I've built an electrochemical cell. And I've got silver plus iron 2, and it's going to iron 3, which is aqueous, plus silver 0, which is a solid, which we've seen already. If we break this up into half cells, we've got silver going to silver 0. And then we've also got iron. Let me put the states on here since that's kind of what the point is. We have iron 2 going to iron 3. So this is our reduction. This is our oxidation. This is going to be the cathode. And this is going to be our anode. All right, so what's different about this, aside from just the fact that we're using iron, is that the anode reaction, wrong color, the anode reaction has something aqueous going to something aqueous. So you can't build an electrode out of, iron plus 3. Nothing has changed at the cathode. We're just using silver, and we can still use a silver electrode. So how will we build an electrochemical cell out of this? So we would leave much of it the same. We put in a salt bridge, we have our beakers, we're separating out our 2 half reactions, etc. Over here at the cathode, we're still going to use silver. We have this wire set up. Potassium nitrate in the salt bridge. Okay, but what are we going to use for our electrode over here? So if we come back up here and look at this one, right, we used zinc metal, which was being oxidized to zinc plus 2. So what we ideally would use, right, we would build this out of iron plus 2. But we can't build an electrode out of an ion. So if it has a charge on it, we can't make an electrode out of that. It's not a metal, it's not going to conduct. Well, it's not a metal, so it's not just going to form this like nice solid that we can kind of shove on here. And you can't just use like iron chloride or something. That's not going to conduct or do kind of the same chemistry. And so what we use is we use a platinum electrode. So platinum is an inert electrode. So it doesn't actually participate in the chemical reaction. It just serves as a conduit for electrons to flow to or from. So in this case, we have the electrode, the platinum electrode is at the anode. And we have this reaction that'll happen in solution where we're starting with iron 2, and then it's going to iron 3. And so here, where it's iron 2, as it goes to iron 3, it just kind of hands its electron off to the platinum electrode before it gets oxidized to iron 3 over here. So it starts out as iron 2, and it hands off its electron to kind of become iron 3. And then that electron can travel along the wire until it gets to the silver, where the silver can now kind of deposit on this electrode over here. And so the reaction is happening, the whole reaction at the anode is happening in solution. So iron is just getting oxidized to iron 3. And then the platinum electrode over here is just sort of this inert thing that serves to pick up that electron and transfer it over to the cathode. That's all it does. So if you have a solution, so if the question is when do we use a platinum electrode, cathode or anode, it doesn't matter. It's when you're going from an aqueous to an aqueous, whatever you're looking at. So here we're going from aqueous iron 2 to iron 3. So we want to make sure that we use a platinum electrode here because you have to. If you don't have something where you're going to or from a solid, then you can't use. How do we get iron in solution as a reactant? Yeah, it's always a salt. So you would dissolve in like iron nitrate. So you'd also have nitrate or something in here. Silver, we'll put nitrate in there as well. It's always going to be a salt. You can never dissolve in like a pure, just like a singular cation or anion or something. You always have to have some sort of spectator ion. Like if you go and you want to buy iron, like let's say you want to buy iron 2, so you're doing a reaction with iron 2. If you go on a chemical website like Sigma Aldrich or something, what you'll see when you look it up is you can't just buy iron 2. There's all these different salts of it. I can buy iron chloride, I can buy iron nitrate. I don't know, I could buy like iron acetate or something. But I can't buy just iron plus 2. So when you see iron 2, for example, over here is drawn in, if I haven't written anything out over here, it doesn't mean that there's no anion in solution. It just means that I don't want to clutter things up by drawing an anion in. And so you want to just pick a counter anion here that's not going to be involved in the chemical reaction, something spectator-ish. Yeah, that point about like, what's going on with this counter anion and this idea of salts, students kind of half get that, I feel like, and struggle with it well into organic chemistry. So yeah, so if we want to draw out the shorthand notation for this, it's the same kind of idea. We just want to put platinum out front. So I'm going to put platinum with a little comma, and then I'm just going to draw the oxidation half reaction. So we see iron 2 going to iron 3. I have a salt bridge there, and then I have the reaction that's happening at the cathode, which is silver, which is then going to go to silver 0. Okay, so now I've just got an extra little thing here, the platinum that sits on the outside. Let's see. The iron be inside the line or outside the line? I'm not sure. Like you're saying, what if I drew it like another way you could draw this is be like this? Is fine? Is that what you're asking? Either one is fine. Does that answer that question? Inside with a comma. I don't know. In my notes, I have a line. I'm not sure. I think this is fine if you want to draw it. You're saying like this, like.
Because they're both in the aqueous, right? And there's no phase boundary between them, except the platinum, which is solid.
I guess that. I mean, I think that's fine as well. Yeah, if these are supposed to represent phase boundaries, maybe a comma is fine there. Let's see what McCord writes. It has a PhD in electrochemistry. Let's see what he has on his website. Yeah, I don't know. On McCord's website, he has a little line separating them. I vaguely remember from when I took general chemistry like a trillion years ago when I was an undergraduate, us using a comma there. Either one is fine. Just kind of be familiar, yeah. It can be a line, let's say it can be a line or a comma. I don't know what the IUPAC or like, standard the agency that kind of standardizes all this stuff. So I see I have a textbook next to me. Strangely has no shorthand with it. That's not helpful at all. Anyway, either one is fine. You can draw it this way, you could draw it this way. Maybe just be familiar with both. The main thing, at least when I think about these, is just that the order that you kind of draw things in is probably the most important. Like iron 2 is going to iron 3, silver plus is going to silver 0. There's some salt bridge in between. And then if you have a platinum electrode, you kind of write it on the outside. So for example, if the platinum electrode was on the other side, we just write it out over here. With the lines and the commas and stuff. Maybe I should be more concerned with that, but I've seen those written a bunch of different ways. So I've never thought of them as being a phase boundary. If that's true, then yeah, I agree with you about just putting a comma there. It makes a little more sense. Okay. So anyway, so we use platinum. The main takeaway here is that we use platinum when we have something where it's aqueous, and we can't make a solid electrode out of whatever it is we're trying to oxidize or reduce. All right, so this takes us to something that we've kind of seen before. Not exactly, but so standard hydrogen electrode. Physical chemist, you know, when you're working with free energy or anything to do with thermodynamics, and even kinetics for that matter, there's an interest in sort of standardizing and tabulating things so that you can kind of have these big tables and sort of do simplified calculations. So when we looked at like free energy, remember we had like standard free energy, standard enthalpy, all these different types of things. And that way, as you sort of add to the growing body of knowledge around those things, everybody's kind of on the same page. You're using, it's like in physics when people talk about reference frames, everybody's using the same reference frame. So in electrochemistry, a reference frame for sort of free energy or whatever you want to call it, potential energy differences between two different species is something called the standard hydrogen electrode. And so in these experiments, what we want to, which we end up doing, is you take a platinum wire, so this is platinum electrode, and you set that up in one of your half cells. And the reaction that you look at is just H plus going to H2 gas. And this is, your proton concentration is around 1 molar. And then over here, you have something else that you're trying to kind of measure it against. So the idea here is that the idea here is, so what you can do is we can measure the number of, you put a voltmeter across here, and I always use this standard hydrogen electrode over here, and I can take the anode over here and just change it out. So I could put in, silver or lithium or any variety of metals as the anode, and I can measure the voltage across the anode and the cathode. And since I'm keeping the cathode constant, like the reaction that I'm doing at the cathode constant, I sort of can tabulate all of these different types of things, and I have sort of a nice comparison for how easily something is going to be oxidized or reduced So let's take a look at what that looks like practically. So if I have a silver, which the thing we've been using is the anode. If I have silver over here, and I wanted to measure its, and I wanted to, like, I guess, measure its standard oxidation potential, I guess is what you call it, I would set up this experiment here. I guess we've been using this as the anode, but as the cathode. It doesn't matter though. But if I wanted to measure the sort of the potential energy associated with this reaction here, so where I have silver at the on the electrode over here and it's being oxidized to silver plus, I would measure it against the standard hydrogen electrode over here, and I would get some sort of voltage out of it. And that voltage would be this. This is not exactly how you'd set up this experiment, but yeah, maybe silver's a bad. It's fine. Anyway, let's just keep it simple. We'll say that we measure this voltage that's negative voltage, and that's fine. But yeah, we'd get this, and then we could swap this out and put something else there, like lithium, which would have a large positive voltage, and we start tabulating those things out. And if you look on the GChem website, I think within the little like module for it, you'll find one of these charts, which basically indicates that somebody's gone in and done these reactions. This is, usually these are put in terms of reductions. So here, you'll note that we're looking at the oxidation of silver 0 to silver plus, and the voltage is negative. In the table here, the voltage is positive, but that's just because I flipped it around. So now I'm looking at the opposite of that reaction. So if I flip a reaction, the voltage is just it's the same magnitude, but it has opposite sign. If you look at, actually, I can post the link in the. There's a larger table, here it is. There's a larger table of standard reduction potentials that you can look at. So for like any kind of metal or redox reaction you can dream up, I posted that in the chat window, there's some sort of reduction potential that you can see. Look up for it. So these are called standard, standard reduction potentials. You know, there's taking under standard conditions, which are 25 degrees Celsius, and you're using, that means that they're taking at 25 degrees Celsius and you're using this standard hydrogen electrode over here. So that's what this is measured up against. So you'll notice that at the top here, these things that are large and positive, so the more positive the voltage, the more spontaneous, I think that's an okay way to say it, the more spontaneous the reaction. So if you look at this table over here, you'll notice these are all reductions because the electrons are on the reactant side. That's kind of how we think about reductions. And so these things at the top are very easily reduced. If I take fluorine, I can add 2 electrons and make fluoride. That makes sense, right? Fluorine's in group 7. We know group 7 wants to pick up electrons to become like noble gas configurations. If we look at lead, okay, so lead plus 4 is easily reduced to lead plus 2. Chlorine is easily reduced to chloride. These all have positive voltages associated with them. As we hit here, right, 2H plus 2 electrons goes to hydrogen gas, we see that that is the reaction that's described in the standard hydrogen electrode. And so if we're comparing, that means that you've, instead of having silver over here, for example, you've set up the same thing. I've got platinum and I've got H plus, and it's at 1 molar. What's going to be the voltage across that? It's going to be 0. There's no potential energy difference because I'm comparing the same thing. It's like saying, you know, what's the difference in gravitational potential energy between 2 objects that are the same mass? If I've got like an amble at the top up here and an amble at the top up here, and there's some, so they both weigh 1 pound, and there's some distance from the ground down here. They're the same distance, same mass. What's the gravitational potential energy of both? It's exactly the same. That's sort of the thing that's happening here as well. These things are identical. You know, where does the electron prefer to be? Is it going to prefer to be over here or here? It doesn't have a preference because they're exactly the same. And so what do we expect our potential energy difference there to be? Nothing. And so we see that there's 0 for the voltage. So the standard hydrogen electrode sort of defines this scale over here, which is somewhat arbitrary. Once you cross over here, though, where the voltages become negative, that means that these things are not very easily reduced. So going from iron 3 to iron 0 is not spontaneous, at least against the standard hydrogen electrode. Going from lead +2 to lead 0 is not spontaneous. So when we put it in here, and this is, when we put it inside of, when we try and do this reaction up here, you would see that it doesn't happen. Is sort of what the implication is of a negative voltage. It won't happen spontaneously against the standard hydrogen electrode. And so that's kind of how to read this. That's kind of what this table is useful for. We can tell if the, let's see. So if you're looking at a particular, let's say one more thing. Let me talk about this. How do we know which lead or iron half reaction to use? Yeah, you look at the oxidation number. That is good advice. Yeah. So you're always, so remember these things have a lot of different oxidation states. So you always have to look at the charges here. Like iron 3 going to iron 0 is different from iron 3 going to iron 2, which is the one that we just looked at. So look at both sides of the reaction and make sure that you match the charges to whatever you're looking at. The only other note about this table, which is kind of what I've already said. So I said that things at the top are easy to reduce. That they have positive voltages. That's for standard reduction potentials. Things at the top are easy to reduce. That means that things at the bottom are hard to reduce. And so if we want to put that in a different terminology that we'll use in electrochemistry, we could say that these have increasing strength as oxidizing agents, which is another way of saying that they're easily reduced. And these have increasing strength as reducing agents, at least on this side, which is another way of saying that they're easily oxidized. So things down here tend to be easily oxidized, and things up here tend to be easily reduced. You'll notice that I'm going to the other, when I talk about things that are being oxidized, I'm all looking at the product side of these reactions. So the oxidation reaction happens going in this direction, backwards. If I say lithium is easy to oxidize, which is what this negative voltage implies, that means that the backwards reaction is spontaneous. So up here, where we're looking at this, since it's positive, it's saying, well, the reaction goes very easily in this direction. But down here, it's saying, well, this reaction, it doesn't go easily, and that's why this is negative. But the backwards reaction, we know, would be positive 3.05. And so that one goes quite easily. So lithium is easily oxidized. That's what we know from looking at a group 1, right? Remember group 1 on the periodic table. These are things that want to lose electrons so that they can have a noble gas configuration. And so it's not shocking that the oxidation is easy, but the reduction is not. And it's the same kind of thinking as looking at these group 7 things. The reduction of fluorine is easy because they want to pick up electrons. That's why we see this positive voltage over here. But so the nice thing, the reason that people go through and tabulate these values is because it allows you to very quickly say whether or not a reaction is going to be spontaneous or not. So if we look at, so usually you're not, we're not just doing these hydrogen gas reactions. So the voltage relative to what does plus 2.87 mean with respect to the hydrogen electrode? That's what we're talking about, right? We're saying, well, that's that voltage. But usually we're setting up a reaction that's different. Like if we come back up here and look at silver, I can look it up. If we look at this reaction from the top, well, actually, let's look at, let's start here. We can use this equation. If we're trying to look at two half reactions and tell if the reaction is going to be spontaneous, we can say E naught for cell is going to be equal to the oxidation potential plus the reduction potential. Another way of saying this is to say that it's equal to E cathode minus E anode. They're all kind of the same expressions. But so if I take, like, let's say, let me try and find one that matches electron-wise. Let's say I have iron and copper. So I want to take copper plus 2, and I want to have that going to copper 0. So that would be the cathode. But the reduction is happening. And let's say that I want to say, well, what if I mix that with, let's pick something else with 2 electrons on it down here. What if I mix that with iron 2, and I want to have that at the anode, but I want that to be my oxidation reaction. Oh wait, no, we're going to iron 0. Yeah, let's say I'm taking iron 0 now and I'm oxidizing it to, I want this to be my anode reaction. That's my oxidation. Is this going to happen? Like, will this happen spontaneously? So will I measure a positive voltage if I set that cell up? In order to figure that out, I could just use these equations up here. So I could say, well, I can take the potential, the oxidation potential, and subtract it from the reduction potential. So let's start there because I think that's more informative, even though it's not the easiest way to solve it. So I would say E cell is equal to the oxidation potential. What's the oxidation potential going to be? So this is the oxidation reaction, is iron 0 going to iron plus 2. So I come up here and I look at my table. These are reduction potentials. This is written going as a reduction. So it's saying I take iron 2 and 2 electrons to get iron 0. We want the oxidation potential, so we need to flip that sign. How do I know that I want the oxidation potential? Because that's how this reaction is written out. It's the opposite of this reaction. And then for the reduction potential, that's just going to be what we look up in the table. So that's copper. So I have copper here going to copper plus 2 going to copper 0. You see that that matches this equation I've written down here. And so that's plus 0.34. And so I end up with, what is that, plus 0.78 volts. The other way to do it is to just look at, you can use this reaction equation. So this would be a spontaneous reaction because it's positive. That's really the extent of thinking there. But if we look at this one here, it's just E cathode minus E anode when you're looking at standard reduction potentials. So what's happening at the cathode minus what's happening at the anode. And that sort of fixes the sign without having to think about doing the switch. So we could say E cell, we look up the cathode reduction potential, which is here. We say, okay, that's 0.34. And then we want to subtract it. We want to subtract out the reduction potential that's happening at the anode, which is right here. So minus 0.44. Those are both in volts, and we end up with the same answer. So it doesn't matter which one you use. This one takes care of the sign for you. This one you have to kind of do it in your head, but it's a little more informative. So you can see these, sometimes you'll see these tables written out as standard oxidation potentials. Now everything's going to be flipped where the electrons are going to be on the opposite side, and that'll flip all the signs and the voltages. So that's a good question. Would this be an electrolytic cell? No. So galvanic cells, it's called a galvanic cell as long as it's spontaneous. So if the voltage is positive. It's an electrolytic cell if it's not spontaneous. And we haven't quite gotten there yet. We'll get there in next class. But it's an electrolytic cell if it's not spontaneous. And then, yeah, so that means that you have to do work on the cell in order to get to flow back. So for like a phone battery, for example, it's a galvanic cell when it's discharging as you sort of use your electronic. So you're sort of harnessing the work of those electrons as they flow from a high potential energy state to a low potential energy state. But eventually that reaction gets finished and comes to equilibrium. So now the voltage difference between the two half cells in the battery are 0. And so you need to charge your battery up. and then your phone battery becomes an electrolytic cell. So you plug it into a wall socket and you use the wall socket to do work on the battery and push those electrons back uphill so that you can use your battery again. So yeah, galvanic is spontaneous, electrolytic is non-spontaneous. That's when you're doing work on the battery itself. Okay. So anyway, so that takes us right up against, I think, the Nernst equation. I'll send an announcement about kind of where I expect you to kind of be for the exam after Thanksgiving, and what we'll do on Monday, so that that's really clear for what to study. But certainly, at the very least, you should be able to kind of. It's not this week coming. Obviously, it's not Thanksgiving week, but it is the week afterwards, and then we have a couple of more classes, and then we're all done for the semester. So yeah. So Thanksgiving, try to relax some, and then probably over the weekend you'll have to start studying, depending on how much you've already studied. Yeah. All right, let me take a quick break, and then I'll see you guys in office hours. All right, do you guys have any specific questions? Quiz 2 on homework 9. Let's take a look, see. Question 2 on homework 9. Balance the skeletal equation of hydrazine with chloride ions shown below. The reaction takes place in basic solution. What is the smallest possible integer coefficient of chloride in the balanced equation? All right, this one will probably take us a second or two. Okay, so you're starting out with. So this is one that we probably wouldn't see in like a galvanic cell type question. Like usually you're dealing with metals and such in there. You could set something like this up, I guess. Maybe if you had a platinum electrodes at both sides, but you've got hydrazine on one side. That's what this N2H4 stuff is. Is that true? I'm not sure what N2H4 is. Whatever it is, it's probably not something. It probably causes things to blow up. It looks like jet fuel or rocket fuel. And we're adding that to chloride. And we're getting NO out of it. Nasty stuff. And then we're getting a little bit of Cl minus. And they're asking us to balance it. So this is one of the ones where you kind of have to go in and do a little bit more in terms of figuring out the oxidation states for what's being oxidized and reduced. So chloride is negative. There's nothing really interesting about that. Oxygen we know is going to be -2. So that means that the nitrogen is going to be +2. And then when we come over here, we see that chloride has a net negative charge, which you know. So we know that the oxygen should have a -2, so that's -6. And so chlorine must be +5. And then hydrogen over here is going to be +1, so that's +4. We know this thing has to come out to be 0, so that means that nitrogen must be +2. Something's right here. Chlorine is being reduced. Let's see. So this is changing. What happened to the hydrogens? Did I lose something here? I guess the hydrogens will get balanced out when we balance out the H+ or whatever. Something's up. Oh, thank you. Jesus. Yep, that's right. Positive plus a positive does not equal 0. Nitrogen should be -2. Okay.